Alright everybody, let's go ahead and get rocking and rolling on that midterm review packet. So today I'm going to try and get through the first few sections that we didn't cover yesterday. So starting with section 4, the instructions say write each expression in terms of log base 3 of A, log base 3 of B, and log base 3 of C. So I'm going to do maybe one or two from this section here. If we look at, say, something like number 21, that seems to be the one that kind of stands out the most to me right now. If I say log base 3 of a to the 6th times b to the 1/4, ultimately, what you have to understand is that this problem is just asking you to separate logarithms. So how do we do that? Well, if I have two answer pieces that are being multiplied inside the same logarithm, I can split that logarithm up into two separate logarithms. And from here, I would just bring down those answers' respective exponents. So what I get ultimately would be 6 log base 3 of A plus 1/4 log base 3 of B. And that's really as far as you need to go. You just need to, separate them out. That's all you got to do. So those are the instructions for section 4. Section 5. I'm looking at this. Let's say we look at something like number 27. Section 5 says simplify and write as a single logarithm. Well, if I look at 27, it goes 4 log of P minus 3 log of Q plus 2 log of R. Now, before we move forward, remember, if I don't have a discernible base at the bottom of each of these logarithms, I assume that it's base 10, right? So they all have the same base, which means I can combine them out. I'm going to go and use the reverse of the last rule. I'm going to go and just kick all of these numbers in and make them the exponents. So what I have is log base 10 of P to the 4th minus log base 10 of Q to the 3rd plus log base 10 of R squared. So from here, a couple of things are at work here. I've got 3 logarithms, 2 of which are being subtracted, 1 of which is being added. So what I can do is I can consolidate this into one logarithm of a P up top to the 4th divided by a Q on the bottom, since they're being divided, and an R squared on the bottom. And that's as far as you need to go. Whoa. Cool, so let's take a look at section 6. So section 6 is exponential equations. So we'll start off with something kind of easy like number 31. We've got 4 to the x is equal to 6. And so the first thing I always ask is there any way that the 4 and the 6 can be made to have the same base? I don't think so. And so if there's not any discernible way, I like to take the natural logs of both sides. So what I get is the natural log of 4 to the x equals the natural log of 6. I can use some exponential rules to kick this guy down. I get x natural log of 4 is equal to natural log of 6. Remember, natural log of 4 is just a number, so I'm going to go and divide that out. And I get x being natural log of 6 over natural log of 4. Now, before we move forward, this is what we consider calculator ready form. From here, I see the same mistake happen. People think that you can reduce and make this natural log of like 3 over natural log of 2, but that actually does not happen because these two will not simplify out. Remember, you got to order your do things by order of operations, and the logarithms would have had to have happened first before dividing anything out. So that's not what that equals, so please don't make that mistake. Let's go ahead and do another one from this section here, like perhaps number, say, I'm looking at maybe 37, where it is possible that the base is, actually no, let's do 38 instead. Oh no, I've already written down 37, forget it. Where it's possible that the bases can be made the same, I think. 1 over 25 to the 8th power. And I think we can mess with this a little bit. I know that I've got 5, 5 to the x squared minus 8x is equal to, I can call 1 over 25 5 to the negative 2, and that will be taken to the 8th power. Still, that 8th power didn't go anywhere. So I got 5 to the, I don't know why I did that, ridiculous, x squared minus 8x is equal to 5 to the negative 16 now. And now from here, because the bases are the same, the exponents can be made the same. So x squared minus 8x is equal to negative 16. And so from here, I'm going to set this thing equal to 0. So I've got x squared minus 8x plus 16 is equal to 0. And I think this thing can be factored into x minus 4 and x minus 4. So x really just equals positive 4, and you're good. All right, let's take a look at the next page. Alright, so let's look at section 8. It says, find the first 5 terms of the sequence and determine if it's arithmetic or geometric, and then do a bunch of other stuff with it. So, if we look at 51 here, if I said a sub n is equal to 6n minus 10, well, let's find the first 5 terms. For that, I don't really need a formula. If I plug in a 1, I'm going to get negative 4. If I plug in a 2, I get 2. Right, because 6 times 2 is 12, minus 10 gives me the 2. If I plug in a 3, I get 18 minus 10, which is going to be 8. If I plug in a 4, I'm going to get 24 minus 10, which is 14. And actually, I think you guys are starting to see a pattern here. It looks like I'm adding 6 every single time. So without even having to plug the next number in, we should hopefully guess that the next number is going to be 20. Okay, well, if we're adding 6 every single time, that means that this is none other than an arithmetic sequence, because we're adding something each time, right? And now we need to express the nth term as some kind of a sub n equals a sub 1 plus n minus 1 times d. So, well, we know what d is, right? We know that in this case, d is equal to 6. We know that a sub 1 is equal to negative 4. And the thing is that we don't know what n is, but that's okay, because we're actually just writing the general formula for this. So n really is just n. Right? We're looking for any single term in that sequence. So I know that a sub n, which is any term, that's going to be a sub 1, which is the negative 4, which is what we found when we plugged in a 1 into the n area. Plus d, well, that's going to be plus 6 times n minus 1. Well, that's just n minus 1. So if I wanted to find the 70th term, I would just plug in 70, and I'd be good to go. And that's as far as you need to go for 51. Right, nothing else to it. Okay, so let's go ahead and take a look at section 9. We'll go ahead and do 57. It goes like this. It goes 100, 90, then 81, then dot, dot, dot. Now, oddly enough, it doesn't seem like it's growing or shrinking by any kind of pattern, because it looks like we're subtracting 10, then subtracting 9, then who knows what's happening after that. But if you look really closely, if you wanted to figure out what r was, what you would do is you could do 90 divided by 100 and find out what that answer is. And then you could do 81 over 90 and find out what that answer is. Okay? Well, from here, what you get is you get 9/10 out of that, right? And then, oddly enough, if you divide both top and bottom by 9 here, you also get 9/10, which means r is equal to 9/10. Now, how did I get that again? I used division each time, which means if we're dividing or multiplying by a number that's smaller than 1 and greater than negative 1, we'll get a common ratio as long as that stays the same all throughout. And at this level in math, there is no reason to suspect that suddenly it would move into a different direction. It's always going to be pretty consistent. So if r equals 91, that means that we automatically have a geometric sequence right here. So in order to find the next two terms, what I'm going to do is I'm going to multiply 81 by 9/10. Well, the next term is going to be 81 times 9 over 10. Well, what's that going to be? Well, that's going to be 729 over 10. Well, that's my next term, 729 over 10. And the next term after that is going to be 729 over 10 times 9/10 again. Well, I know I'm going to get a 100 up top, and 729 times 9 is going to be 6561. So these are the next two terms in the sequence that you're looking for. So we've already solved part B. Now time to solve part C. Find a sub n. Well, a sub n is that general formula, right? So a sub n is equal to a sub 1, which was 100, times r, which was the 9/10 to the n minus 1. Well, since I'm trying to find the formula for any term in the sequence, n minus 1 is just n minus 1. And that's all there is to it. All right, let's move on to the next section. All right, section 10 talks about finding the sequence, arithmetic or geometric series described. So 62 through 67 is relatively obvious. They're giving you all the information right away. Where people are going to make their biggest mistakes are going to happen from 68 through 75. So let's go and take a look at something like 70 real quick. So it looks like I've got 6 plus 13 plus 20 plus 27 plus ... plus 97. So from here, what you want to identify first is what type of series are we dealing with? Well, we can tell by looking at the distance between each numbers. It looks like it climbs by 7, and it looks like we're adding 7 every single time. So if I put d equals 7, then I think that's a pretty safe bet. We also know that a sub 1 is equal to 6. N is the only thing that we don't have. Right? So if I wanted to sum this up, I would say s sub n is equal to n over 2 times a sub 1 plus, in this case, a sub n would be the last term, so that would be where the 97 comes in. All I need is the n right here. Well, how do I find that out? Well, I'm going to go ahead and use my sequence formula to find out what n is. Well, I know that sequence formula is the a sub n is equal to a sub 1 plus d times n minus 1. So if I look at really closely, I know that a sub n is actually 97. It's the last term in the sequence. A sub 1 was 6, which is what we started off with, plus d, which is the 7, times n minus 1. And n is the thing that I'm solving for. So if I go and subtract 6 from both sides, I get 91 is equal to 7 times n minus 1. From there, 91 divided by 7 is going to give me 13. So I get 13 is equal to n minus 1, so n is equal to 14. And that's the number that goes inside here. So s sub 13 is equal to 13 over 2 times, looks like 103. So from here, it's a little bit of calculator work. If you don't know what 13 times 103 is, it should be 1339 divided by 2. And that's really as far as you need to go. Not exactly the best number, but it's something that works. All right, let's take a look at a sigma problem here. And so if we look at something like number 71, you start from k equals 1 to 6. The formula is 2k plus 11. So you can expand the first couple terms. So if you plugged in a 1, you would get 13. If you plugged in a 2, you'd get 15. If you plugged in a 3, you'd get 17. So I think we kind of see the pattern here. It looks like we're increasing by 2 every single time, which means I'm thinking that this is probably some kind of arithmetic series. Now, I'm going to go and plug in a 6 into here. What do I get? Well, I get 12 plus 11. That's 23. So 23 is my final term. 13 is my first term. If I know what these are, then writing this using Gauss's formula is pretty easy. S sub 6 is going to be 6 over 2, because n is the number of terms you have. You count from 1 to 6, you get 6 terms. And then 13 plus 23 is going to be the magic number. And so 13 plus 23 gives me, looks like 36 times 3. We're looking at a sum total of 108. And we'll go ahead and hold off on infinite geometric series since that carries over into the next page. But as long as you know what a convergent versus divergent ratio looks like, you should be okay. See you guys tomorrow.